Welcome back, everyone. We're going to continue our journey into chapter 10. We're going to be doing section 10.5 that deals with the rotation of conics. So conics is what we've been doing, the parabolas, the ellipses, the hyperbolas, and now we're going to be dealing with the conics that have been rotated on the x and y axis. Okay, so how do we know if you're dealing with a rotation of conics? Well, this is your general one that we discussed in the last section. If A and C were the same, then you had a circle. And then if A times C was equal to 0, then you had yourself a parabola. If A times C was positive, then you had an ellipse. And if A times C was negative, then you had a hyperbola. But how do you know if you have a rotation? Well, it's simple, because you're going to be adding another factor, which is the bxy. Notice here how I went from A to C and then D, E, F. Or if any of you guys notice that there was a B missing, this is where the B is. If you have a bxy, that means you have a conic that is rotated on the x and y axis. All right. So there's a couple of things, like you already know how to graph a parabola. You already know how to graph an ellipse and a hyperbola. Well, all we need to do is get this equation, this one right here, and then make it look like this equation, and then we can go ahead and just graph it the way that we normally would, but on its rotated axes. So this is what I'm talking about here. You have the x and y axis, your traditional horizontal and vertical, which are these guys right here. This is your y-axis, this is your x-axis. And then now all of a sudden you have a conic with the bxy term, right? Which means that there is a theta rotation, all right? So now the x-axis is rotated, so now that's how you get the x prime axis, and then the y prime axis. So you literally take the x and y, and then you're going to rotate it whatever theta is, which we're going to learn how to calculate. And now a traditional ellipse, let's say, looks like this, right? But if it's been rotated, then it's going to look like this, right? Which looks like an ellipse, but the formula will have an xy on it. But that's the main difference between a standard or the general. When you look at the general equation, if you have a bxy term, then you are talking about an ellipse that has been rotated. So there's a couple of things to know. You have the general, right, equation here. Oops, you have the general equation here. Because we have this term right here, we can rewrite it in a way that we have this equation, which is, it has a bunch of primes there, but essentially if we ignore those primes, then you have your traditional ax squared plus cy squared plus dx plus ey plus f equals 0, which we already know is a conic. Okay, so how do you find theta? Well, all you got to do is solve this equation. All right, and a is coming from the equation that we have been given. So this a is this coefficient minus c, this coefficient, over b, which is this coefficient. All right, and now you solve cotangent of 2 theta, which cotangent of theta is 1 over tangent, which is cosine over sine, right? So a couple of things to know. So once you have theta, okay, once you have theta, then we can use that to make our substitutions, which we have on the bottom. The coefficients of the new equation are obtained by making the substitutions x equals x prime cosine of theta minus y prime sine of theta. So you're going to substitute x with this, the new one, because you have found theta. And then y, you're going to substitute it with x prime sine theta plus y prime cosine theta. So now you have your x and your y. You take this substitution here, put it into this equation, do the math, and you're going to end up with an equation with primes. And that's going to be your conic, but when you graph it, you're going to move the axes theta units. You're going to rotate it theta units. All right, so what does that look like? So let's do this quick example. Go ahead and pause it so you can work it out. Over here on the top right hand side, I put all the information that you need. But go ahead and pause it as I work this out and I explain it. Alright, so the first thing we want to do is to go ahead and extract what we need to find theta. So we look at the formula on the right. It says cotangent of 2 theta equals a minus c over b. So we know a equals 7, b equals negative 6 squared of 3, and c equals 13. So we plug that into the formula. So we get cotangent of 2 theta equals 7 minus 13 over negative 6 squared of 3, which equals 1 over the square root of 3. So now you have to solve cotangent of 2 theta equals 1 over the square root of 3. So then one thing, like however you solve this, right, it's going to be up to you. But one thing that you should be thinking of when you see the square root of 3 is the 30, 60, 90. So when you have a 30, 60, 90 triangle and you have cotangent or tangent, that means you have a ratio between them. So because the square root of 3 is on the bottom, we have 1/2 over the square root of 3 over 2. And then we use the identity for cotangent, which is cosine over sine. Alright, so how does that help us? Well, it says, when is cosine equal to 1/2 on the unit circle? So you go to the unit circle, you locate the x value of 1/2, and it turns out that cosine is 1/2 when theta equals pi over 3. But because we have, in other words, cosine of pi over 3 is 1/2, right? So that's what we need. So, but we don't have just theta, we have 2 theta. So in other words, cosine of 2 theta, right? Let me erase this. So that means, in this case, theta is pi over 3, but we have 2 theta. The double angle, so that means that theta is pi over 6. Alright? Just keep in mind that you have the cosine of 2 theta. Another way of solving this would be for you to do cotangent of 2 theta equals 1 over the square root of 3, which means 2 theta equals the arc cotangent of 1 over the square root of 3. Now if you have some type of website to give you the exact answer, then that's what you're going to go with. But it turns out that this guy right here is pi over 3. So for theta, we get pi over 6. So we have theta equals pi over 6. So now that we know what theta is, then you plug it into the formulas which are on the bottom of this little block I put here where we're eliminating the xy term. We get the following, and now this I had paused the video, but it took me like 45 minutes to come up with the solution because I had missed the negative sign the first time, and the second time when I did the distribution of everything I lost track of one of the variables. And so one thing I do recommend is, as you're working this out, what's going to end up happening is the xy term is going to be eliminated. Hence, that's what it says in the top right hand corner. We're going to eliminate it, but just keep everything in fraction form. Don't try and simplify the fraction right off the bat. Just keep everything, just the numerators. Don't simplify anything until the very end. So it's going to be important for you to track everything to just ensure that you get the right answer. And you're going to know you get the right answer because you're going to have some nice numbers. You're going to have some nice fractions when you divide by the constant. Well, I mean, in these problems, they're going to work out nicely. So we do have this formula that says x equals x prime cosine of theta minus y prime sine of theta. And then the other formula is y equals x prime sine of theta plus y prime cosine of theta. So all you're going to do is plug in the values. You know what theta is, so you're going to do x prime cosine of pi 6 minus y prime sine of pi 6. So once you do that, then you should have it, leave it in this form so that it'll be easier, right, for you as you are distributing everything. Okay, I think it's easier to keep it in this form as opposed to two separate fractions. We just have one big fraction. And then for y, you should be getting x prime plus the square root of 3 y prime over 2. Alright, so that's what x and y are. So now what you're going to do is take x and y, those two fractions, and you're going to plug them in to this equation right here. Alright, and this is where the work, where you have to be real careful, and it gets very tedious, but be careful with all the variables. You have a lot of primes. If you want to start using just x and y, by all means do that, but you know, just take your time with these problems. So at the end, once you do everything, distribute everything, you should get x prime over 4 plus y prime squared over 1 equal to 1. So as you can see, this is an ellipse. A equals 2, B equals 1. We have your x and y, but now it has been rotated. What was theta? 30 degrees. So now it's going to be x prime, y prime, pi over 6. So as you can imagine, you can extract all the information. It's going to be at the origin, and a is equal to 2, and it's going to be opening more on the x, so it's going to go 1, 2, 1, 2, and it's going to go up 1, down 1. So it's going to look something like this. Rotate it. And then one last thing I want to mention, similar to what we did in the last section, where you look at the coefficients and you find out whether it's an ellipse, parabola, hyperbola. Here we include the b factor and we do the discriminant where it's b squared minus 4ac to determine which of the following conics you're dealing with.